Hello, class. I would like to lecture on chapter A. So chapter A, you will learn about complex number, how to add, how to subtract, how to multiply, how to divide, and the polar coordinate. You will learn about the form, the standard form of it. How does it relate to rectangular coordinate? How do you convert back and forth? How you graph? You will learn in this chapter A. Okay, let me see. Okay, I'm sharing my screen. Recording. Okay, I have everything. Okay, let's look at the summary. So the summary is so we'd like to focus on I will show you the form of the complex number. You will learn more complex number in pre-calculus. However, so I can show you like a bit in details how to work with a complex number. So the complex number, as you notice right here, we have the definitions, right? But in short, in general, the form of the complex number is, let me annotate here. The form of a complex number all the time will be a plus bi. So that's what you need to know. Remember, a and b here stand for the real part, which is they are all real numbers. Like real numbers can be decimal, can be square root, can be a fraction, can be anything. Okay, but for the we have two parts for this complex number. As you notice, let me use different color. So you got that part we call real part. And we have the complex part will be this part. We call imaginary part, or some people call fraction parts. And I think just call imaginary part. I think complex, the fraction part. I remember something else. So the real parts and the real part and the imaginary part. The imaginary part, because why is have the imaginary number I. I is the imaginary number, and I stand for I is equal to square root of -1. Okay. So so let's look at the definitions. The number I is such that I squared is equal to -1. But actually, I is square root of -1. So I square equal to square root of -1, everything square. Okay, everything square. And then that become -1. The squares are just cancel the radical. So you have -1 stay. And so on. So the purpose you only need to remember is I or I square. The if A in this case, so they say if A, this value A, is greater than 0, then the expression square root of -A can be written as I times square root of A. Actually, you don't have to remember that part. You only need to remember is I equal to square root of -1, and I squared will be equal to -1. And you also need to remember the complex number have the form is A plus BI, where part A we call real part, and the part have i's in that, which is BI, so that part we call imaginary part. That's all that you need to know. Okay, and sometimes let me give you an example like this. An example. Oh, they do have the example on the left. They do have the example on the left. So they have 1, 2, 3 form. Okay, so they all call complex number. Why? Okay, let me explain why. So look at the example on the left. So each of the following is a complex number. The first example is 5 plus 4i. 5 plus 4i, we are having 5 as the real parts. And the imaginary part is 4i, right? And we are having the following, the second example is negative square root of 3 plus I. So the real part is negative square root of 3. The imaginary part for that example is plus 1i. Okay. The next example is 7i. So 7i here, we all only notice that the imaginary part only. But you don't forget is if I add 0 plus 7i, so that become a form of the complex number. So that's why 7i is still considered complex number. Negative a is similar. So negative a, they are having the real part. The imaginary part you can imagine is like you add with 0 times I. So then we are having the form of the complex number. So that's why all of this called a complex value, complex number. So that is for the definitions. Any question, please email me. And the next concept, the next part is we call equality for complex number. What is it? Okay, let's erase this first. Equality is equal, right? Complex number, this complex number equal to the other complex number, right? That's what I said. So now look at the definitions. If you have two complex numbers that are equal, if and only if their real part are equal, and the imaginary parts also equal, and we are having the form of, let's say the first complex number is a plus bi. The second complex number is c plus di. Okay, so in this case, these two complex will be equal if and only if a have to be equal to c and b have equal to d. Okay, so that's the case. So the example for this one is, so if I obviously give you the number, for example, like let's say 1 plus I, for example, it's obvious, right? So that have to be equal to 1 plus I, right? So, and if there's some like more general example, maybe on example 2, they are having, if they have the equation 3x plus 2i equal to 12 minus 4yi, so that's mean the real part of this, okay, which is 3x have to be equal to 12, and 2i, or which is 2, right? So b equal to d. So 2 equal to 2 minus 4y. Remember when they have the subtraction or something in the front, you have to bring that along. Then they set up two equations like this. Then you will solve for x and y. If you replace x and y back into the original equation, which is 3 times 4 is 12, plus 2i, so that would be equal to 12 minus 4 times minus 1/2, right? So that will give us plus 2 and then I. So when they have the general equation like this, you want to solve for x and for y, that's easy way you do it. So next part is the operations on complex number in the standard form, which mean they teach us how to add, how to subtract, how to multiply, how to divide complex number. I'm sorry, it's a bit noisy because they have the dump trucks. Okay, let me move down. All right, so the example 3 is very good, but first look at the general formula for the complex number. Okay, so we have addition. Addition, when you add two complex numbers, it means you add the real part with the real part. The complex part, the imaginary part with the imaginary part. But remember, see that? They factor out the small r, they factor that out. They just take the part, the real b, to add to one another, and then keep the i's one time. Or in other words, you say combine like term, right? So B1I plus B2I, they are combined like term. So that means B1 plus B2. And they got I in common. So for subtraction, it's just the same thing. You got a real part subtract of each other, and then you add with, uh, the imaginary part subtract each other. The multiplications, for multiplications, you need to do FOIL. Okay, you distribute each part in, okay, like this. Later you look at the example, the real example, then you will understand better. So in short, for multiplying the complex number, you do FOIL. Okay, for example, like this. If I have, let's say, I'm not use A because you might confuse. I might use X plus Y times X plus Y. Right? For example, like this. You do FOIL is mean you take the first part, you time with the first part, take the first part of the first parentheses times the second, and then take Y times this, and then take Y times Y, like that. And then you do combine like term. You got the value. Similar to complex number, you do FOIL and then you combine like terms. Okay. For the for next, they talk about conjugate. Okay, they talk about conjugate. It mean you see A plus BI will be the general form, the standard form, have a plus. The conjugate, would you switch the plus into the minus? Okay, and all the time their product will be A squared plus B squared. It's just like this. If I have X plus Y times X minus Y, this gives me the form of X squared minus Y squared. It's just similar, okay? So this time, they just give you the very general like this because the I here timed together give you -1 and -1. They have the minus in front, they would cancel out. So that's why they just, give you directly the form of A squared plus B squared. Later I will demonstrate from the example, then you will see it. Okay. Next, well, division. Division, you take the first complex, divide the second complex. In order to do divide, um, the complex value is just like you're thinking about a square root. So we don't, to simplify, they don't want us to leave the square root at the bottom. So you try to do somehow to make a square root on the top. Similar to the complex value, you try to do somehow to make I on the top only, not at the bottom. And then you simplify. So, and the demonstration will be on the left example. Then I will demonstrate a bit more. The example number 3, they give us if Z1 is 2 minus I, then Z2 will be 4 plus 3I, right? So let's add. So to add this 2, got a real part which is 2 plus 4 which is 6. Minus, right? Minus I plus 3I. So this give you like combined term you can thinking of, okay, plus 3 have the higher higher value than that. So you take 3 minus that, give you plus 2. And I you keep the same combined term. Z1 minus Z2, you do the same thing. Z1, if they set up like Z2 minus Z1, then you have to take the value from Z2 minus Z1. Okay, so this time they want us to do Z1 minus Z2. Then you got 2 minus 4 give us minus 2, minus 1I minus 3I give you minus 4I. That's the algebra. And remember, when at the complex number all the time, you have to make the result become a standard form of the complex value. So multiply. So here they do multiplying. Let's see. They do FOIL. It takes 2 times 4, give you 8. 2 times plus 3I give you plus 6I. You're done, right? So now minus I. Minus I times 4 give you minus 4i. Minus I times 3i give you minus 3i squared, remember? Okay, so now you do combine like term. 8 here, so how come is here have real number, but then here's 11? Watch. Because of this. So what I square is what? I square is minus 1, right? So let's go back. Okay. So that's you should remember, right? So I is square root of minus 1. I square will be minus 1. So I square is minus 1 and time minus 3 give you plus 3. Correct? So plus 3 times plus 8 give you plus 11. That's why you got 11. Plus 6, now to come back to me. We got plus 6i minus 4i. Combine like term give you 2i. Then that is standard form. The conjugate just easy. You just make the positive side become negative and you're done. So when they multiply the conjugate, you got a squared plus b squared, right? So which means we have 4 squared, which is 16. And b in this case is 3, right? So 3 squared is 9. Add together, give you 25. And division, you just multiply the conjugate at the bottom, which is in this case is 4 plus 3i at the bottom. You need to multiply top and the bottom by 4 times 4 minus 3i. So then you distribute on the top, which is 2 minus i times 4 minus 3i. You do FOIL, right? When you do FOIL, then you having the value 5 minus 10i. The process to do FOIL, you look up here for me, please. You practice doing it. And then the bottom we have a squared plus b squared give us 25. And then when you split this, you have 5 divided by 25 minus 10 divided by 10i divided by 25. Then you simplify, we have 1/5 minus 2/5 I. So that's how you do for the complex number. Again, if you want to learn more about this, so please redo this example and practice over, okay? Spend time doing it if you want to learn about this section. In pre-cal, you're not going to learn a lot. In pre-cal, it's just like you know how to recognize the form, how to add, how to subtract, how to times. Actually, you should like understand, you know, kind of the basics like this for a complex number. Okay, and we have the power of I. The power of i's. Actually, like I said, you only need to focus on what is I and what is I squared gonna be. Then from there, you can, you know, multiply and based on, because here they said the power of i's. So remember the power, you just simplify I squared raised to another power, then you can figure out a value quickly. Like right like here, we got I raised to 20th equal to I squared, right? So you remember I squared is -1. And then, you know, I squared raised to 10. So -1, which is the negative value, raised to an even power. The answer all the time will be the positive. If the raised to odd, then you will have -1, okay, and so on. And remember for here, then we are having, I'm sorry, it's depend too, right? So, and over here we have I raised to 21. So for the power here, I'm recommend that you be careful when you are writing down. For example, if I'm doing like this, because I20 we already have the answers, we already know that step, right? So for I raised to 21, I can do like this, I20 raised to 21. So that gives me, okay, I squared, okay, I split that out and I have because when they have the same base, you add the exponent, right? So I'm trying to make the same base. So I raised to 2, that's what I remember is -1, and the leftover is I11, right? So I11, um, you can do I11 like this, but then you see, okay, I11 is still high to you, right? You can break it down more and more and more, just keep breaking down, okay? So doing this, it's even a bit longer way than that one, because when you want to focus on like I square only, then you're gonna do like this. And then okay, you know, I square is -1. You can, okay, you can have -1 time with I raised to 10. You can have like, okay, you can break it down to I square again if you want, and then the leftover will be I raised to 9, right? Or you can do I raised to 8, okay, raised to 8, and then time I. It's still okay, still the same, right? If you want to do like that, and then you break it down, I for this I square again will become -1. So this might become a positive now. So the leftover will be what? I raised to 8. Another word is I square raised to 4, right? So this is the power raised to a power, and then multiply by I. And you know that I squared is -1 raised to 4 is mean not -1 time -1 time -1 time -1 4 times. That's a positive 1, right? Positive 1 time I will be I. So actually, you can do many ways that you want, as long as you understand, like you remember I squared is -1, then I think you'll be okay. Okay, for the graph the complex number. Graph the complex number is similar to graph the rectangular coordinate. So what do I mean? The y part here stand for the imaginary part. So which mean x will be all the time will be the real parts. The real part stand for example, here you got 4 plus 3i. So it means the real part, that's positive 4. You got 1, 2, 3, 4. Example, right? You got 4, value 4 right here. That's the real part, and the imaginary part will be 1, 2, 3. Okay, then you got, connect them. You got this part. That part will represent for 4 plus 3i. Similar with a negative value, you just like using the same steps. Thinking like y will become imaginary part. Then you just take the value in the front of I, then you'll be okay. Then you're done. Okay, so that is the complex number. Okay, what next? Absolute value of the complex number. Absolute value of the complex number, what does it mean? So you think complex number will in a form, so all the time in math, they want z to be, when they call complex number, they want to present z as the value, and z will be equal to a plus bi. So for this complex numbers mean you will find a distance from the origin point a comma b, right? As you know, this is a plus bi, so a comma b, the origin from that point. So which means you would have square r, the radius r, will be equal to the absolute value of z. Then that will be equal to square root of a squared plus b squared. In another word, when you find the absolute value of any complex number, that will be equal to square root of a squared plus b squared. And this way is the form of r, as we learned before. Okay, so that's our r. All right, so the argument of the complex number. So actually, for this one, if you already found r, you know r from the complex number that are given us, all the time you find r. And if they want us to find the argument of a complex number, in this case is actually can be 6 strict, sine, cosine, tangent, cotangent, cosecant, secant. However, you only need to focus this main three, which is sine, cosine, and tangent, then you can figure out the other three, okay, by using the formula. So, and for this case, they want, they might given us the complex number, and then our job, they want you to find the argument of z, denoted by the following: sine theta, right? Sine theta. So you will have that it will be equal to b, which is in the form a plus bi. Okay, so b divided by r. So you have to firstly you have to find r. Cosine theta will be a divided by r, and tangent will be b over a. B over a. Okay, if the argument of z is denoted by theta, then we are having those three or six if they're asking us for more. And the example on the example 7, you notice that z equal to square root 3 plus I. So in this case is theta is the smallest positive angle for which we have sine theta equal to 1/2. And why do they have 1/2? So first they have to find r, right? So in this case, as you notice, sine, cosine, we are having the bottom is number 2, so you can find r from here using this value to find r. Okay, so using that value you have to find r. Then what do you have? You got square root 3, right? Square root of 3 plus 1. Okay, so because square root of 3 square will be 3. So but then the radical here will be the general, like the general radical. So we're having like double of it. But then plus 1, which is I in front of I is 1. So 1 square is 1. That's why we are having square root of 3 plus 1, which is square root of 4. Square root of 4 give us R is 2. And we are having the value B, which is 1 minus divided by R, which is 2. And so on. You are having that. For trig form of the complex number. Okay, so the complex number would, but we have to write in the trigonometric form. Then, so this is our complex number, right? So for the trig form all the time, you will relate that to R. So this is, it's like the rectangular coordinate. It's kind of like that. And the different form for trig, we are having polar coordinate form. It's kind of like that. And we are having z equal to r. So again, you must find r from z equal to a plus bi first. You have to find r, you have to find cosine theta, you have to find sine theta, and then you write in this form, which is r times cosine theta plus I times sine theta. Then you have in the form. These two forms are similar, but they have different way to writing it. If they want us to write in trig form of the complex number, then you write like that. Or the complex number in the standard form, then you write z equal to a plus bi. Okay, so theta in this case will be the argument, which is the angle. And r will be square root of a squared plus b squared. That's all. Again, if you have question, please email me. Part 3, we having product and quotient in trigonometry form. So for part 3, let me see. We know the form of the trig form of the complex number already, which is r times cosine theta plus I sine times theta, right? So we are having that form already. So, but this form, if they raised to power n, which is z raised to power n, then we are having, we call it the Morse theorem. Okay, so the basic is okay. We don't have high power, but if we do, then the form is right here. If they do, we have the form right here. You see that? If they have the raised to n power, then the radius will raise to n power as well. And you got n times with the argument and plus I sine n times theta. And you just need to write like that. Then you have, we call the Morse theorem. All right, and how to multiply, you can notice that for product or quotient, what do? We have R times R, right? So they all, the look like the argument, they add together, right? The argument they add. So how about the quotient? They got the radius R1 divided by radius 2, and the argument will be subtraction, the subtraction, okay? The after when you got the see the example on the left, when we're having this, what do? If for cosine and sine we got the special argument, then you right away got the value. But if it's not, then you can using calculator to figure it out. Cosine 50 is what? Otherwise, leave it as is. 8.4 not necessary. So 8.4 is just very, very rare. I haven't seen this in pre-cal, so you don't have to. Okay, you can spend time reading on this if you want. Otherwise, you don't have to. So 8.5 is what you need to know at least a bit. Polar coordinate. For the polar coordinate, they talking about the order pair. It's not x or y, right? X comma y we call the rectangular coordinates. You learned before, you know that already. So for polar coordinate, you will convert back to r, which is the radius. If they don't have it, then you have to find it from the complex value, from the form a plus bi, or you have to find r. And then you have to find the argument theta. You have to figure out what is theta. And then from there, for theta in this case, all the time, we have two types. We have counterclockwise, which is the argument will be positive, and clockwise will be the argument will be negative. Okay, so let's read over these definitions. The order pair parentheses r comma theta names the point that is r units, okay, r units, which is the distance from the origin, okay. R units from the origin along the x, along the axis rotated through theta degrees, which is the argument, from the positive x-axis. The coordinates r and theta are said to be the polar coordinates of the point they name. So let's look at the example. So all the time when they're talking about polar coordinate, then you have to figure out what is r, what is theta. Okay, theta in this case, like I said already, in the standard position. All the time, for example, on the left side, number 12. So you start from here at 0 degree. I'm sorry. Right, this is 0 degree, and then you go the other way. You go clockwise, or the counterclockwise will be positive angle. So for this case, let me see how many examples they given us. They got 1 point, 2 point. They only have 2 point, which is 2 example. So the part right here represents for polar coordinates. The part right here represents for the polar coordinates. Okay, let's look at the example clearly. So the first pair that we notice is 3, 120. So how do they draw it? So first you got the xy axis, right? So all the time you got the xy axis. And now from there you name it. So I recommend that you draw the angle, you estimate the angle. Okay, cool. So we're estimating the angle 120 degree. 120 degree is counterclockwise from here, right? So all the way go to there. So we got that would be the angle. So you draw a line, or you don't have to. Okay, so we found that the angle is 120 is right there. And then 3 is the radius. So you count from here to here is 3 units, just estimating it. Okay, then you having 1, 2, 3. Actually, we estimating this time, but to draw exact, they do have the special graph, something look like this. The special, they have many circle, stand for like 1 unit, 2 unit out, 2 unit, and so on like this. Okay, but I don't really mind, I don't care. As you can estimating it and just draw it out. Make sure that you understand the direction. Okay, so that point we have R is 3, which is 3 unit out from the origin with the angle 120. Then you have that point. So we got the first order pair of the polar coordinates. The second example is down here is negative 3, comma 45 degree. So look like 45 degree is a positive angle. However, the unit is the negative value. Then what do we do? So let me grab this. I'm gonna trade this along. So first you notice, you draw 45 degree from the standard position, which is from 0 here and go up here is 45 degree, right? So you got the angle, but the radius is negative. I'm sorry, not the radius, R units. We should call R units, or some people say radius. But why is negative? So if it's negative, if it's point up here, 3 unit, then it will become at 3 comma 45, right? But now it's negative value, so you do the opposite. You like protect that value, become negative. Got negative 3 comma 45. That's how they draw it. Okay, I think we will have more example from the textbook. You want to look at it, okay, or maybe in the video from XYZ they have more. Then you can practice doing it. That's how they graph that. Okay, what is it? Polar coordinates and rectangular coordinates. Okay. So now they want us to convert back and forth, huh? So let's read this. To derive the relationship between polar coordinates and rectangular coordinates, we consider at point P with rectangular coordinate x, y. Like I said, rectangular coordinate have the form x comma y, but polar coordinate we have the form r comma theta. So these two we have the same point, the same position, okay, the same point, the same position. But then in order to convert or something that we have the way to do it. So let's look at that. We have x comma y, we call that rectangular coordinate, which is right there, right? R comma theta will be the same point, but in the form of r comma theta, which is polar coordinate. Again, for x, y, you already know that already. It's obvious, right? You got x value, how many, y value, how many, and then you dot, 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 dot. You got a point. But for r, comma theta, you have to find the angle, and then you find the r units to get that point. So let's do an example on the left, number 13. Let's convert negative square root of 2, comma 135 degree to rectangular coordinates. How do we do that? We do have the point x equal to r times cosine theta. So I don't know if we went over it. Okay, so they didn't mention. Okay, it's okay. So so this might be new to you too. All right, so do having the form, we have r, x will be equal to r times cos theta. So this formula we did from chapter. I think chapter 3 or 4 in the past. Another word, do you remember? Cosine of theta equal to x divided by r. You know this? You recognize this? So that's why if we find x, we got will be r times cosine theta. That's the formula is from there. Okay. And y equal to r times sine theta. What do? You just plug it in. You just plug it in and you got a value. By using over here we are having, okay, plug in negative square root 2, right? Negative square root 2, plug it in for r, time cosine theta, theta in this case is 135, right? 135. All right, so now we solve for x. Similar, we solve for y. So in order to solve for x, we got, so what do? We focus here. We got negative square root 2, already have it given. Cosine 135, you have to using reference angle to figure out a value. Okay, so 135, let me see. Let me remind you. We have this circle, right? Unit circle. So 135 is in what quadrant? 135 is in quadrant 2. Because here is 0, here's 180. 135 is in quadrant 2. So this is 90, right? 90 and plus 45. 90 plus 45 is 135. So using reference angle, you are having this will be what? 45 degree, right? 45 degree, cosine of 45 degree is square root 2 over 2, correct? Square root 2 over 2 or 1 over square root 2 is the same thing. And then what do we have? Negative. You have negative for cosine 135 because it's cosine in quadrant 2, right? This is in quadrant 2. Cosine in quadrant 1 and 4 will be positive. Cosine in quadrant 2 and 3 will be negative. That's why you have the negative value. So when you simplify, you will have positive 1. You do similar steps for psi, for y. Then we are, but psi in this case is positive because it's in quadrant 2. For psi is positive value when it's in quadrant 1 and quadrant 2. So that's why you have a positive. Now you are having y is negative value, which is negative 1. So the rectangular coordinate will be 1, comma, negative 1, right? So to draw that, then you can just draw regularly, right? 1, negative 1, you dot, put a dot. So the value, which is we having negative square root 2, 135. So like I said, if you want to draw that points, then what do you do? You got 135 degree. You draw that first, which is from here to here, right? From here to here, 135 degree. And then the negative square root 2, which is the projection from that branch. So because it's negative, so you go backward. So square root 2 is 1. Square root 2 is what? It's 1 point something. Let me wait for a minute. 1.4, right? So you go from the origin out 1.4. Okay, this is diagonal. That's why you don't have exactly 1 unit like for on X or 1 unit for on Y. Okay, so you got from the origin out will be 1.4. Or like I said, they having, you can estimate drawing it, or we are having the graph like in circle shape and you draw it. So you are having, that's how you convert from polar coordinate to rectangular coordinate. All right. You can do backward, right? You can do backward to figure it out. If they given you x, y only, right? And they want you convert into the polar coordinate, what do you do next? What do you do first? You have to find r, you have to find theta, and then you combine in the form. Then you having the what they want you to do. More example would be in the I think in the lecture video from XYZ or from the textbook. You want to look at it. So let me see if they have example on it. Okay, they do have example on it. Let me see. Equation in the polar coordinate. Okay, change x plus y equal to 4 to polar coordinate. Since x is equal to r times cosine theta and y equal to r times sine theta, we are having r cosine plus r sine theta equal to 4. Okay, then factor out, I got r. So actually you don't have to do this one. Okay, so just convert polar coordinate and rectangular coordinate, that's it. All right, class, so let's watch the video together. If you have any question, please let me know. Video chapter A. So let's start with the complex number.
In this section, we're going to look at complex numbers from an algebraic point of view. Here's our first problem. We want to find x and y if this complex number is equal to this complex number. Now this number has the form a plus b times I, and this has the form c plus d times I. And the only way two complex numbers can be equal is if their real parts are equal. So I'll set 5x plus 2 equal to 4, and if their imaginary parts are equal, negative 7 equals 2y plus 1. I'll solve this equation for x by adding negative 2 to both sides and then dividing by 5. So I get x is equal to 2/5. I'll solve this equation by adding negative 1 to both sides. I have negative 8 is equal to 2y. Then I'll divide both sides by 2 and have negative 4 is equal to y. So in order for these two complex numbers to be equal to each other, it must be true that x is 2/5 and y is negative 4. And the point of this problem is that two complex numbers are equal if their real parts are equal and their imaginary parts are equal. Here's our next problem. Let's simplify this sum and difference of complex numbers. We're going to treat the I, even though we know it's the square root of negative 1, just like it was a polynomial. Or we're going to treat all of these expressions as if they were polynomials. So I'll start by taking care of this subtraction sign by changing the sign of each thing inside the parentheses. So I'll have 3x, I'll have 3 plus 2i minus 6 minus I plus 5 plus I. So I remove these parentheses. There's a negative sign in front, so I change the sign of each thing inside. Now let's see, I have 3 plus negative 6 is negative 3, plus 2i minus I is just I, plus 5 plus I. And I'll continue to add the real parts. Negative 3 plus 5 is going to be 2. And then I plus I is 2i. So I've simplified this complex number, this expression right here, involving three complex numbers down to just the complex number 2 plus 2i. And I did it by treating everything as if they were similar terms. So I add the real parts which don't have the i's in them, and I add the imaginary parts which do have the I in them. Let's look at another problem. Let's simplify I to the 32. Any power of I can be written as I, negative I, 1, or negative 1. And I think I'll use the fact here that I squared is negative 1 and write this as I squared to the 16th, because I know 2 times 16 is 32, and I also know that I squared is negative 1. So I have negative 1 to the 16th power. Negative 1 to the 16th power will just be the number 1. So that power of I to the 32, simplifies to just 1. I to the 33, I'm going to do the same type of thing. I'll write this as I squared to the 16th times I. So 2 times 16 is 32 plus 1, that's the exponent right here, adds up to 33. I to the second to the 16th power I know is 1, times I to the 1 gives me just I. So I to the 32nd power simplifies to just 1, I to the 33rd power simplifies to I. Every power of I, every integer power of I will simplify to either 1, negative 1, I, or negative I. Here's our next problem. Let's expand and simplify 3 plus 2i. So I'm going to write this as 3 plus 2i times 3 plus 2i, using the fact that this exponent means repeated multiplication. Now, I'm going to multiply just as if these were polynomials. So I'll multiply the first two terms, 9, the outside terms, 6i, the inside terms, another 6i, and then the last terms, 2i times 2i will be 4i squared. So this will be 9 plus, now 6i plus 6i. These are similar terms, so I'll add these and get 12i plus 4 times I squared, which is negative 1. So 4 times I squared is negative 1, so this is going to be 4 times negative 1, which is negative 4, plus 9 will give me 5, plus 12i. So if I square this complex number, 3 plus 2i, I end up with a complex number 5 plus 12i, and I do it by treating it the same as if it was a polynomial. So I add similar terms right here to get 12i, and then I also use the fact that I squared by definition is negative 1 to help simplify this last term a little bit. Let's look at a division problem. We have 2i divided by 3 plus I. So to do division with complex numbers, I do something that's similar to rationalizing the denominator with radicals. What I do is multiply the numerator and denominator of this fraction by the conjugate of the denominator. So I end up with 3 minus I times the denominator and 3 minus I times the numerator. So once I have that, now I can just go ahead and multiply. 2i times 3 will be 6i. 2i times negative I will be negative 2i squared. And in the denominator, when I multiply conjugates, I'll have 3 times 3 is 9. Positive I times negative I is negative I squared. A negative I squared is a positive 1. And then my inside term is 3i, my outside term is negative 3i, so those add to 0. So I just end up with 9 plus 1. Now I'll simplify the numerator here. Negative 2 times I squared will be positive 2 plus 6i, all divided by 10. And then I'm going to reduce this to lowest terms by writing this as 2 times 1 plus 3i divided by 2 times 5, because I have a factor of 2 common to the numerator and denominator. That divides out. And so if I want to write this in standard form for complex numbers, this will be 1/5 plus 3/5 times I. Or I could just write it as 1 plus 3i all divided by 5. But if I want to see the real part and the imaginary part here, it will be 1/5 plus 3/5 times I. So that's a look at addition, subtraction, multiplication, and division with complex numbers.
All right. Let's see. Next section.
Next, we want to look at complex numbers written in trigonometric form. And you can see over here on the board, I've written that the complex number x plus yi, its graph will be the vector that goes from the origin out to the point xy. Well, if that's true, then we can let r be the distance from the origin out to that point. That's the absolute value or modulus of that complex number. And then theta is the angle that the vector makes with the positive x-axis. So using trigonometry, then I can derive the fact that x plus y times I is the same as r times cosine theta plus I sine theta. This is in what we call standard form, and this now is in what we call trigonometric form. So if you want to see the actual derivation of this, you'll have to read the book. But it's all based on this diagram right here, which really goes back to our simple definition for the trigonometric functions from either chapter 1 or chapter 2. Let's try one of these problems. Here I've written write negative 1 plus I in trigonometric form. So I have x plus 1 times I. So it's negative 1 plus 1 times I. I have the real part and the imaginary part in standard form. I want to write it in trigonometric form, so what I need is r, and I also need theta. So let's graph this complex number, negative 1 plus I, and see if we can make it easy on ourselves. I'll make this negative 1. This will be 1. So I'll go out to this point right here. This vector that goes from the origin out to the point negative 1, 1 is the graph of the complex number negative 1 plus 1 times I. Well, I know from simple trigonometry and the distance formula that the distance from the origin out to the point negative 1, 1 is going to be square root 2. I also know that this angle right here must be 135 degrees because this vector goes right in between the two axes there. So it splits that quadrant, so that's 135 degrees. Therefore, this complex number, negative 1 plus I, in standard form, must be equal to square root 2 cosine of 135 plus I times the sine of 135 degrees. So trigonometric form for this complex number, square root 2 times cosine 135 plus I sine 135. Let's look at another problem. This time we want to take the complex number 2 times the quantity cosine 30 plus I sine 30 that's written in trigonometric form and write it in standard form. Let's just sketch the graph of this real quick as long as we've got it here. I'll draw a vector at 30 degrees with a length of 2. So there's the graph of that complex number 2 times cosine 30 plus I sine 30. To write this in standard form, I simply look up these values. I'll use exact values right here. Cosine of 30 is square root 3 over 2 plus I times the sine of 30 is 1/2. Then I'll multiply 2 times this fraction, and I'll have square root 3. 2 times this fraction, and I'll have 2 times I times 1/2, which will just be I. So in standard form, this complex number 2 cosine 30 plus I sine 30 turns out to be just square root 3 plus I. And here you can see the graph right here. This means that this ordered pair, xy, that's at the tip of this vector, must be the ordered pair square root 3 and 1. Let's look at another problem. Cosine 210 plus I sine 210. Okay, I want to write this in standard form also instead of trigonometric form. Let's draw its graph. 210 degrees is 30 degrees past 180. So I'll draw it like this. And this has a modulus or absolute value of 1. So I'll make it half as long as that one. So it has a length of 1. And this angle right here is 210 degrees. So if I want to write this now in standard form, I'll simply look these up. Cosine of 210, well, the reference angle is 30 degrees. 210, you can see, terminates in quadrant 3. So I have negative square root 3 over 2 plus I times sine 210. The reference angle is 30. Sine of 30 is 1/2. And in quadrant 3, it's negative, so negative 1/2. So I end up with negative square root 3 over 2 minus 1/2 I for that complex number written in standard form. So going from trigonometric form to standard form is really very direct. You just simply look up the values of these trig functions and then simplify until you get something that looks like it's written in standard form. Let's look at another problem here. Let's write 8i in trigonometric form. We'll go back the other way. Well, 8i is the complex number 0 plus 8i. So from the origin up to the point 0, 8. So I'll just make this 0, 8. There's the graph of that complex number. It's easy to see by looking at this that that length of the vector is 8 and that this angle right here is 90 degrees. So if I want to write this complex number that's written in standard form in trigonometric form, it will be 8 cosine 90 plus I times the sine of 90. So it's just that simple to go from the graph of this complex number written in standard form to the same complex number written in trigonometric form. Now let's work another problem in which we have to do a little bit more work to find that angle. Let's write 3 plus 4i in trigonometric form. Well, let's begin by graphing this complex number. It's the vector that goes from the origin out to the point x equal 3 and y equal 4. So that's going to be this point right here. So that vector looks like that. Now I know that with this right triangle right here, this is 3, this is 4, so this must be 5 by the Pythagorean theorem. So I have r is equal to 5. The only other thing I need to find is theta. So theta right here is going to be the inverse tangent of 4/3. So it's the angle whose tangent is 4/3. Now that's its exact value. I'll look it up on the calculator just to give me an approximate value for this. If I put in 4/3 in the calculator, press the inverse tangent button, I get 53.1 degrees. Let's just round to the nearest degree. So I'll take this value of r, this value of theta, and I'll write 3 plus 4i in trigonometric form as 5 cosine 53.1 degrees plus I times the sine of 53.1 degrees. So I should probably write approximately right here because this angle is not it exactly. The exact value for this angle would be inverse tangent 4/3. But just so that I have something to write, I'll go to my calculator, work this problem, get 53.1. Now I have my complex number in trigonometric form with an r and a theta right here. So this is approximately what it is. This would be exactly what it was if I used that. So there's a look at how we go back and forth between standard form and trigonometric form for a complex number.
That is section 8.2. 8.3 is right here.
Multiplication and division with complex numbers written in trigonometric form is pretty easy. Let's look at the first problem. We want to multiply 7 times the quantity cosine 110 plus I sine 110 times 8 cosine 47 plus I sine 47. Multiply two numbers written in trigonometric form. Very easy. We multiply their absolute values, 7 times 8, and we add the angles. Cosine 110 plus 47 plus I sine 110 plus 47. You don't have to actually show that step. 7 times 8 is 56. Cosine, let me put parentheses in here, 110 plus 47 is 157 degrees plus I sine 157 degrees. So to multiply two complex numbers in trigonometric form, we multiply their absolute values and we add the angles. So 110 plus 47 is 157, and 7 times 8 is 56. Real nice, easy way to multiply numbers. Let's look at division. I want to divide this complex number by this complex number. It's very easy to do so. I'll just divide absolute values. It'll be 18 divided by 12, cosine of, and I'll subtract angles. 51 degrees minus 32 degrees plus I sine of 51 degrees minus 32 degrees. And let's put brackets around that. So I divide the absolute values and I subtract the angles, where the angle in the numerator comes first minus the angle in the denominator. Now let's see, 18 divided by 12, I'll reduce to lowest terms. That looks like 3/2 or 1.5. I'll write it as 3/2 times cosine. 51 subtract 32, what's that, 19 degrees? Plus I times the sine of 19 degrees. So division, very similar to multiplication, except we divide absolute values and subtract angles. Let's look at one last problem where we take a complex number and raise it to a power. We want to simplify negative square root 3 plus I all raised to the 4th power. Now I can just do this problem with algebra by multiplying negative square root 3 plus I times itself 1, 2, 3, 4 times. I use it as a factor 4 times. But it will be actually easier to do if we first convert to trigonometric form. So first of all, let me find r. R is equal to the square root of x squared, which will be 3, plus y squared. Well, y is 1, squared is 1. Square root of 3 plus 1 is the square root of 4, so I end up with 2. Now to find theta, I'll do this. Cosine of theta is going to be equal to x, negative square root 3, over 2, and the sine of theta is going to be equal to 1 divided by 2, so 1/2. So this tells me that the reference angle for theta is 30 degrees. I can look over here and see that since cosine is negative and sine is positive, I must be in quadrant number 2 with a reference angle of 30 degrees. That tells me that theta itself must be equal to 150 degrees. So now I have r and I have theta for my complex number right here, so I can write it in trigonometric form, 2 cosine 150 plus I sine 150, all raised to the fourth power. Now the raising to the fourth power is going to be very simple. So I'll write my complex number in trigonometric form as 2 times cosine 150 degrees plus I sine 150 degrees. Now I want to take this number right here and raise it to the fourth power. Well, I know from my work with complex numbers and multiplication that to raise this complex number to the fourth power, it's 2 raised to the fourth power times cosine of 150 times 4, which is going to be 600 degrees, plus I sine of 600 degrees. So now I have 2 to the fourth, which is going to be 16. Cosine 600, what I'm going to do with my 600 right here is subtract out 1 complete revolution, or 360 degrees. That will leave me with 600 minus 360, which should be 240. So let's just write a little simpler form. Cosine of 240 degrees plus I times the sine of 240 degrees. Now, if I wanted to, at this point, switch back to standard form, I'll simply write down cosine 240 and sine 240, multiply that out, and I'll have my complex number in standard form. But you can see if I want to raise this to an exponent, let's say 4, 5, 6, or higher, what I do is I take my complex number, find r and theta so I can write it in trigonometric form. Then once I have it in trigonometric form, raising to a power is real simple. I simply raise the absolute value to that power and multiply the angle by that power. So there's a look at multiplication, division, and raising to powers with complex numbers written in trigonometric form.
All right, everyone. So we have 8.4, right? And then 8.5, and we're done.
Next up, we want to find roots of complex numbers, and here's what we know. Every complex number has n nth roots, which means that every complex number has 2 square roots, 3 cube roots, 4 fourth roots, so on and so forth. So what I want to do here is look at the 3 cube roots of the number 8. Well, I already know one of those, and that's the number 2. 2 is the real cube root of 8, so let's look at its graph. The graph of 2 will be the vector that goes from the origin out to the point 2, 0. So here's the graph of one of the cube roots of 8, which is 2. This is what else I know about the cube roots. They distribute themselves evenly around the coordinate plane. So I want 3 cube roots of 8. That means that those 3 cube roots are going to divide the coordinate plane up into 3 equal pieces. So I'm going to have one up here at 120 degrees. And then I'm going to have another one down here at 240 degrees. So 120, 240, 360. So that divides the coordinate plane up into 3 equal parts right there. Each of these complex numbers will have a length of 2. And so there's a picture of the 3 cube roots of the number 8. So now what I want to do is, using this picture right here, write them out in trigonometric form and then convert from that to standard form. So let's just look at my first one here. It's 2, which is 2 cosine 0 plus I sine 0. Well, that turns out to be 2 times cosine 0 is 1, sine 0 is 0, so I just end up with 2. I already knew that, but I wanted to go through the process of writing it in trigonometric form, changing it to standard form. Okay, let's look at this complex number right here. It's 2 times cosine 120 plus I sine 120. So I can see that the reference angle there for that, 120, is going to be 60 degrees. So now I'll convert to standard form. This is 2 times cosine 120 is the same as cosine of 60, which is 1/2, except it's negative because I'm in quadrant number 2. So 1/2 plus I times the sine of 120 is square root 3 over 2. I multiply by 2, and I end up with negative 1 plus I square root 3. So there is my second cube root of 8. Here's my first cube root of 8. And now let's find my third one, which will be 2 cosine of 240 plus I sine 240. So that will be 2 times, okay, cosine of 240 is negative 1/2, plus I times the sine of 240 is negative square root 3 over 2. Now I multiply 2 times this, I get negative 1. 2 times this, I get negative I square root 3. So here is my third cube root of 8. So if I take any one of these cube roots right here and cube it, I end up with the number 8. Now let me just show you that you already knew how to solve this problem previously using algebra. So I want to just continue right here and do the same problem with algebra. If I'm looking for the cube roots of 8, I'm looking for values of x for which x cubed equals 8. I write this in standard form as x cubed minus 8 equals 0. It's a cubic equation which I can factor, x minus 2 times x squared plus 2x plus 4. If I set this factor equal to 0, I get x equal 2. When I set this factor equal to 0, I get x equal, I'll have to use the quadratic formula, negative 2 plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. Now I'll simplify this. Negative 2 plus or minus square root of 4 subtract 16, square root of negative 12, all divided by 2. So I have negative 2 plus or minus, when I simplify square root negative 12, I get 2i square root 3, all divided by 2. Now, notice when I take this last expression right here and divide the numerator and denominator by 2, I'll have negative 1 plus or minus I square root 3. When I use the plus sign, I get this solution right here, and when I use the minus sign, I get this solution right here. So my work that I get by solving this problem using algebra corresponds exactly to the work I get when I use my information on complex numbers in trigonometric form and how their graphs are evenly distributed around the coordinate plane to find the cube roots of 8. So pretty simple problem, and a kind of an interesting fact about complex numbers that they have 3 cube roots. Every one of them does. 4 fourth roots, 5 fifth roots. Let's try one more problem. This time I want to find the 4 fourth roots of this complex number right here. And this time, instead of using the graph, I'm going to use the formula that's in the book. So the 4 fourth roots will look like this. They will be the 4th root of 16. So I take the 4th root of this number, and then I multiply that by cosine of, okay, I'm going to take my angle, 120 degrees, and I'm going to add on multiples of 360, because that's what the period is for cosine and sine, and then I'm going to divide that by 4. So 120 degrees plus 360 times k divided by 4, because I want 4 fourth roots, plus I times the sine of the same thing, my original angle, plus multiples of the period, all divided by 4. And then I'm going to do this for k equal, that's this k, 0, 1, 2, 3. And so as I substitute these 4 numbers in for k, I'll get out my 4 fourth roots right here. So, but before I do that, let's just simplify this a little bit. I end up here with the 4th root of 16, that's the real 4th root of 16, which is 2, times the cosine of, okay, 120 plus 360 divided by 4 is going to be equal to 30 degrees plus 90 degrees times k. Because 4 divides into 120 30 times, and 4 divides into 360 90 times, plus I times the sine of the same thing, 30 degrees plus 90 degrees times k. Okay, so I write this out right here. The formula looks pretty complicated when you see it in the book, but it's really just this simple. You take the angle and add on multiples of the period, and then you divide by the number of roots you want, in this case, 4/4 roots. Okay, so I simplify that a little bit. Now I'm going to substitute in k equals 0, then k equal 1, then k equal 2, and then k equal 3, and from that I'll get out my 4/4 roots. So when I substitute in k equals 0, that's going to give me my first root, which I call w sub 0. So that will be 2 times cosine of, when I put in 0 here, I'll get 90 times 0, which is 0, plus 30, which is 30. Okay, so that's my first fourth root. My next one, which I'll call w sub 1, that'll be what I get when I put in 1 for k, so that'll be 2 times cosine of. 1 times 90 is 90, plus 30 is going to be 110, plus I times sine of 120. Thank you. Did I say 110? No, 120. Okay, so 1 times 90 is 90, plus 30 is 120. So I get 2 cosine 120 plus I sine 120. My second one, or my third one, I should say, will be what I get when I let k be equal to 2. Cosine of 2 times 90 is 180, plus 30 is going to be 210. And then my last one, which will be w sub 3, is what I get when I put in k equals 3. 3 times 90 degrees is going to be 270, plus 30 will be 300 degrees. So 2 times cosine of 300 plus I sine 300. Now, we could easily graph these 4 roots of the complex number, of this complex number right here, and you would see that they would be evenly distributed around the coordinate plane, and each would be a vector of length 2. So this formula might look kind of complicated in the book, but in actuality, it's really pretty easy to use, and this is a look at finding roots of complex numbers.
So the last section is, okay, I accidentally erased it. Let's see. I see. Okay, the last section is about polar coordinates. And again, if you have any question, please ask for
The second way to name points in
for section 8.4. You don't have to worry about it, okay?
the coordinate plane is with polar coordinates. Polar coordinates are a little different than rectangular coordinates, and in this section we want to look at how we convert back and forth between them. But first of all, let's take a look at how we graph some ordered pairs in polar coordinates. So I want to graph in polar coordinates the ordered pair 2, 135. So this is the distance out to the point that's on the terminal side of this angle in standard position. So 135 in standard position is going to be the angle that the terminal side of the angle will be along this line right here, and I want to go 2 units out on that. Well, you can see that my units are 1, 2, and 3. So on this line right here, I'm going to go out 1, 2 units. I'll be at this point right here, which is the point 2, 135 degrees in polar coordinates. So in polar coordinates, the first number is the distance out to the point, and the second number tells you the angle in standard position along whose terminal side you travel to get to the point. Let's look at the next one. I have the point 1 and negative 135 degrees. Well, if this is 0 right here, negative 135 is back this way, and that's this angle. And so I want to go 1 unit out on that angle, which is negative 135. So negative 135, and then I want to travel out 1 unit. That's this point right here. So there's the point 1, negative 135 degrees. Next, I have negative 2.5 and 45 degrees. So here's 45 degrees right here. And now this time I want to go negative 2.5 units on that. So that's negative 1, 2.5. That's that point right there. Let me do that in red. That's this point, which is negative 2 and 45 degrees. So I can have positive and negative numbers for both r and theta. Remember, angles are measured positive when I go in a counterclockwise direction and negative when I go in a clockwise direction. So here's the point that's 2 units out on the terminal side of 135 degrees. This is the point that's 1 unit out, 1 unit out on the angle in standard position negative 135, and this is the point right here that's negative 2 units out on the angle 45 degrees. So instead of going forward along 45 degrees, I go back negative 2 units on its projection back to the origin like that. Let's look at another problem. What other ordered pairs name the same point as 2 60 degrees? Well, let's take a look first of all at the graph of 2 and 60 degrees. I want to go 2 units out on the terminal side of angle 60 degrees in standard position. So I'll go 2 units out, 1, 2, on an angle of 60 degrees in standard position. So this is the point right here, 2 60 degrees. How else can I name this point? Well, I could say, let's say I'll name it with a negative angle. I'll get to that angle this way, which would be, let's say, 2 units out on the angle negative 300 degrees in standard position. So this angle is negative 300 degrees, and all I have to do is go 2 units out on that. How about if I also said, okay, I'm going to go over here to, let's see, this angle right here, which would be negative 120 degrees. I could use that angle, and then I could go back 2 units on that. So how about negative 2 units out on negative 120 degrees? Would look something like that. I could also say, how about this angle right here? That would be the angle, what, 240 degrees? And I could go negative 2 units out on it. So negative 2 and 240 degrees. Now, I could also add on 360 degrees to any of these angles right here and name another ordered pair that named the same point right here. So this is one of the things about polar coordinates that's different than rectangular coordinates. Different ordered pairs like this can name the same point. So each point does not have a unique representation in polar coordinates. Let's go on and look at our next problem. This time we want to convert from polar coordinates, square root 2, negative 135 degrees, and into rectangular coordinates. So what I have is this. R is equal to square root 2. Theta is equal to negative 135 degrees. And here's my conversion equations. X is equal to R cosine of theta, which is square root 2 times cosine of negative 135, that's going to be negative 1 over square root 2, which comes out to be negative 1. So square root 2 times negative 1 over square root 2 is negative 1. Y is equal to square root 2 sine of theta, so sine of negative 135 degrees, square root 2 times the sine of negative 135, reference angle is 45 again in quadrant 3, negative 1 over square root 2. I multiply those out, and I get negative 1. So this point, square root 2 and negative 135 degrees in rectangular coordinates is the point negative 1, negative 1. So if we were to graph this point, negative 1, negative 1, we would see that it also can be named by going square root of 2 units out on the angle negative 135 degrees in standard position. So it'll end up in quadrant 3. Its coordinates will be negative 1, negative 1. Here's another problem. This time we want to go in the other direction and convert from rectangular coordinates into polar coordinates. From this ordered pair in rectangular coordinates, I see that x is equal to negative 2 square root 3, and y is equal to 2. So to write polar coordinates, I need r and theta. I know that r will be the square root of x squared, so 4 times 3 is 12, plus 2 squared, which is 4. That's the square root of 16, which is going to be 4. To find theta, I'll note that cosine theta is equal to x divided by r, so negative 2 square root 3 over 4, which is going to be negative square root 3 over 2. And sine theta is equal to y divided by r, so 2 over 4, which is equal to 1/2. So I can tell because theta is equal to 1/2 that the reference angle for theta is going to be 30 degrees. Then I look and see cosine is negative and sine is positive. When cosine is negative and sine is positive, I must be in quadrant number 2 with a reference angle of 30 degrees. All of this together tells me that theta is equal to 150 degrees. So I want to name this ordered pair negative 2 square root 3, 2 in rectangular coordinates, in polar coordinates as the point 4 and 150 degrees. So if I want to get to the same point that's named here in rectangular coordinates using polar coordinates, I'll go 4 units out on an angle of 150 degrees in standard position. So two problems right here. One, we start with polar coordinates, change to rectangular coordinates, and then the next one, we start with rectangular coordinates and we change to polar coordinates.
All right, class, if you have any question, again, please email me. And then this section won't be on your test. However, it's good for you to know about this information. All right. Okay, you have a good day.